Next, we go to the third part of the coordinate system, which is a spherical coordinate system. Now, how can we define a spherical shape? How a spherical shape look like? Here you just imagine a ball. Okay, a ball have the shape like this. It has a round shape. And then the surface facing, okay, in all direction. It's facing, okay, all directions. Something like this. Let's say the center is at the origins. So the surface always facing outward along the R directions. The R direction is everywhere lah. Okay, this is R directions. Okay, that is a spherical shape. Now we want to discuss how to determine the DL. Okay, the displacement, okay, on the spherical shape, and then how to define its surface, okay, the surface area, and then how to define the volume. Okay, let's see. Okay, the variable of interest for spherical shape. Okay, you have to imagine this spherical shape is just like a ball. So what is the parameter change? How to make the sphere to be small or to be big? What is the parameter influence the shape, the size of the shape? Okay, we have three parameters. First, we have the radius r. Second, we have phi. And lastly, we have theta. Okay, the difference is we have theta. What is a phi? What is a theta? Okay. Okay, refer to this diagram. We can see, okay, the phi is basically defined as the increment along this part, the x y surface. Okay, this one along xy surface here, around here. So when it's go around, so we can see here that the range of phi, okay, varies from 0 to pi, okay, all over. And then we have the theta. So the theta is defined from, okay, let's say here from positive z axis, and it's going down until the negative z axis. Okay, this is the range from here to here. So that means the range is from 0 to pi. And another important parameters is radius, because when the radius is small, let's say the radius is small, the ball also small. Or I can draw another bigger one, R2. Alright, so how can we define the DL on the spherical coordinate system? Okay, let's consider a small part of the sphere. Okay, this one, this part. Okay, we have here this part. Okay, this part is basically the increment along r directions, and the increment is dr. So that's why we write as a r cap dr, and then we take this part, okay, the curve here, the curve here. How to define the curve? Okay, the curve can be defined as r d theta, because the curve depend on the radius r, and then d theta, and then the direction is along theta direction. That's why you have r d theta in the direction of theta. Okay, another part is this curve. Okay, this is basically the vertical curve. This is the horizontal curve, this part. Okay, to define the curve, okay, the curve is actually depend on theta and also the phi. Okay, because the curve can be anywhere, okay, around this part, different theta. Okay, it's depend on different theta. So when you go into the top, it becomes 0. So to determine the curve is equal to r sine theta d phi. Okay, that's mean if the theta is equal to 90 degrees, so basically the curve equal to r d phi. Okay, like we define for the cylinder. Okay, so because when we take at the on the xy axis, okay, when I draw back, this is x, this is y and x. So I said that the theta varies from, okay, the top to bottom, right? This is 0 degree. This one is 180 degree, or pi. So at the middle here, so on the xy axis is become 90 degree. That's why this expression sine theta, r sine theta d phi, will become r d phi. Okay, so this curve is equal to r sine theta d phi. So what is the vectors? Okay, it's basically is going in these directions. So this is a phi directions. That's why we get here r sine theta d phi in the direction of phi. This is how we define the dl for spherical coordinate. Okay, there is a differential displacement, and then how to define the differential area. How to define the area? What is the area exists on the sphere? Okay, here we give 3 different area, which is dsr, ds theta, and ds phi. Right. For dsr is easy because dsr is basically the surface on the surface of the sphere. So it's around here. This is the surface. The surface of the sphere, okay, is going towards the other directions, in all directions. So that's why we have r dsr, and we have to define what is a dsr here. And when you learn in secondary school, you know that the surface area of the sphere is become to 4 pi r square. So by using this principle, you later on you will obtain this 4 pi r square, the surface of the sphere along facing the r directions. So to define this, so the surface area, okay, along the surface of the sphere is basically equal to r sine theta d phi multiplied by r d theta. Okay, r sine theta d phi and r d theta. So that's why you obtain here r square sine theta d theta d phi. And then we have ds theta. So the surface is facing theta directions, and then the surface is ds theta. It's just like you imagine that we cut the sphere, okay, into the theta directions. How is it? Okay, let's say I have this part. It's just like a piece of pizza, for example. So this is the area. Okay, this is facing theta lah. Theta. So to determine the surface area that facing the theta direction is depend on the, here we have dr, and then we have here r sine theta d phi. Okay, the curve. The curve is actually r sine theta d phi. So that's why we get here the surface facing theta is basically r sin theta dr d phi, because we have dr and multiply by r sin theta d phi. So you got r sin theta dr d phi, and is facing the theta directions. And how about the phi directions? The phi direction. How can I? Okay, I just cut like this lah. Okay, something like this. And this is a phi directions. It's going in horizontal part lah. So here we have also dr, and we have another curve. So you have to differentiate between this curve and the previous curve. Okay, this curve is basically curve here. This is the curve. Okay. So the curve is basically r d theta, and it also depend on dr. So that's why you got here in the direction of phi, we got r d theta dr. Okay, there's a three different area, whether it's facing the phi direction, theta direction, or facing r directions. And the volume, okay, you know that the volume of the sphere, okay, V equal to, if we have full sphere, the volume is equal to 4/3 pi r cube. This is what you learn in your secondary school. But how can we obtain this kind of formula, 4/3 pi r cube? Okay, so basically it's equal to r sine theta d phi multiplied by, we have r sine theta d phi, the first curve, and then we have r d theta, and then we have dr, because the volume is depend on the radius. So it's different with a DSR, because DSR here we don't have dr component, because we want to know only the surface. We want only the surface area. But here we have volume, so we have to determine three dimension. The first part, second part, and third part. So r sine theta d phi multiplied by r d theta multiplied by dr. So we got here dv equal to r square sine theta dr d theta and d phi. Okay, when we set the limit for theta from 0 to pi and phi from 0 to 2 pi, when you solve the integration, the triple integration here, you got this 4 over t pi r cube. But we can cut the sphere into several part, so that's why the volume can be different, so be careful. Okay, this is just the introduction of the del operation. Del operation is the vector differentiation operator. So later on in our next topic, you will see the del operator, and this is how we define the del operator in Cartesian coordinate. We have d over dx in the direction of x, and so on. And then for the cylindrical and spherical coordinate, we can change the del operator. And the del operator will be given during your test and final exam. Because you will be given a table. This is, for example, the table for, we have 4 here, which is a divergence, curl, gradient, and also Laplacian. So these 4 functions will be used in a different chapter for EMT. So you can see here, okay, we have first the divergence. Okay, is equal to del AS over dx plus del AY over del Y, and this is for Cartesian. All here is Cartesian. And then this is for curl. Normally curl is used in magnetostatic, the curl. And then we have the gradient. Gradient is in Malay is kecerunan, gradient. We have gradients. And then lastly we have Laplacian, del square V. The Laplacian will be used in chapter 6. When you want to solve a problem related to the boundary condition, you want to determine the expression of capacitor. So we use a Laplacian later on. This is a Cartesian, and then this we transform into cylindrical coordinate, and lastly the spherical coordinate. Okay, you can see that there are a lot of functions here, but normally to solve the problem, so not all component exist. Maybe only 1 or 2 component exist in the same time, in one time. It depend to the problem. Okay, depend to the problem or question given. So detail for this table, how to use it, will be discussed later on. Okay, so we finish chapter 1. So thank you.